Testing. Welcome back, class. We're going to be looking at section 9.4 today. We will complete it, and so I'll be assigning this 9.4 on this day, Friday. It'll be due then next Wednesday, which I believe is April 8, if I'm not mistaken. Just some background of where we're heading today. When we found our Z statistic, when we looked at sample means, what we did in our numerator of our Z was X bar minus mu. That was our numerator. So it looked like this, X bar minus mu. And we divided by our adjusted standard deviation, S over the square root of n. If you recall, when we looked at confidence intervals for proportions, we also looked at p hat corresponding with our sample mean. What that meant was, now when I'm finding a Z for proportions, which is what this section 9.4 is on, it's about hypothesis testing for proportions, we'll be calculating a Z. Rather than X bar, I'm going to be using a p hat. Rather than mu from our null and alternative hypothesis, I'm going to be using a population proportion P. We'll be dividing by that adjusted standard deviation, which we use with our confidence intervals, and that was the square root of PQ. Q could be 1 minus P all over N. That becomes our statistic now when I'm going to be doing hypothesis tests for proportions. I've written that right here as well. Notice both are Z's. The Z up here was for means. It meant that N had to be greater than or equal to 30. What makes a Z available for us with proportions is not whether N was greater than or equal to 30, but rather, you recall, it was NP greater than or equal to 5, or N times 1 minus P, the complement, greater than or equal to 5, written like that. These have to be binomial populations. I'm in favor of candidate A, I'm opposed to candidate A. Two choices, hence binomial. I'm in favor of Proposition 13, I'm opposed to Proposition 13. Two choices, hence binomial. Let's run an example to see what it all entails. I'll give you a chance to read through that. What you see here is we have 370 out of 500 that responded in one of two ways. It's two ways. They can either say, yes, we were better off, or no, we were not better off. It's binomial, and it's about a proportion. Just like we did with confidence intervals, I'm going to need to find a p hat early on. It's that same X over N that it was earlier. In this case, 370 out of 500 felt that their financial fortunes were better than their parents. So 370 out of 500. It gives me p hat to be, in this case, 0.74. Let's make sure now we understand what we're actually looking to test. 78% felt they were better off financially than their parents back in 1984. 2019, 0.74 are saying that. 0.74 is less than 0.78. Has this percent or proportion, has it gotten less over these years? We recognize 0.74 is less than 0.78, but is it far enough smaller that we have evidence, mathematical evidence, to say that it actually has decreased? Does it give strong evidence to suggest a decrease? That's what I'm wondering if I can show. Decrease is screaming at me, single-tailed test. We're going to run both, again, a critical value and a p-value test. So here we go. Critical value first, and a p-value over here. Step number 1, my null and alternative. I'm trying to suggest a decrease. That's going to be my alternative, a decrease. It's not going to be mu because that would refer to a mean. This is a proportion. So I'm going to say the population proportion is decreased from the 0.78. That means that my null must be the population proportion. It's either equal to, or I could say greater than or equal to. I would accept either one from 0.78. Step number 1 over here would have been the same. Step number 2, I have to list my alpha level. They didn't give me one here. So the fallback is alpha is 0.05. Same for both. Next, I need to determine if I have a large enough sample size. To do that again, you recall I'm looking at either NP or NQ has to be greater than or equal to 5. P is the larger one. In this case, I have an estimate of the population, which I should be using 0.78. So P up here is equal to 0.78, which means Q would be 0.22. Q is the smaller one, so I'm going to use NQ to be greater than or equal to 5. N is my sample size, 500, times Q, which I just said to be 0.22. Notice I'm using the estimate of the population of what it was. I didn't use 0.74 in its complement. I used 0.78 in its complement. Well, that is definitely going to be greater than 5. It's going to be around 100. So I can state here NQ is greater than or equal to 5, which means I'm using my z-stat. I have the same thing over here, NQ greater than or equal to 5, which means I'm using my z-stat. I need a rejection region over here. RR for rejection region. What actually is it? Well, again, I have that drawing. What I'm really testing against is the proportion of 0.78. I'm looking at only one tail. Notice it's less than 0.78. Less than is implying to the left. So I have one line in the sand. That's going to be my rejection region right there. That rejection region has a probability of 0.05, which means this has a probability of 0.45. Well, again, I know you've seen this before, but 0.45 falls exactly in between those. So the z-score is 1.645, right in between. But because it's on the left side, it's a negative 1.645. That's my line in the sand. The rejection region is on the left side of that, less than that. So my rejection region is z is less than a negative 0.1645. Notice if this is less than that, the z should be less than a negative. Had this one up here been greater than 0.78, then this z would have been greater than a positive. It would have been on the other side. Make sure that those two correlate as they're supposed to. Now I go to step number 3. I need to calculate the z-score, but notice this formula is for a proportion. P hat minus the population proportion. This P is right up here like it has been in the past. I have that adjusted standard deviation, PQ over N. P hat we found, it's the sample proportion, 370 out of 500, 0.74. Minus the population estimate, that's the 0.78 out of your hypothesis. Now we have to make that decision again. What do I put in for PQ? Do I put in the 0.78 or do I put in the 0.74? Because this is an estimate of the past, that's what I'm going to be using. I don't have proof that it's changed yet. That's what I'm trying to show. So because I have no proof that it's changed, this P goes with the 0.78. Its complement 0.22, all divided by the sample size 500. Again, you need to be able to calculate that out. Turns out to be a negative 2.16. Again, make sure you can do that because that'll be crucial on your test. Negative 2 is less than a negative 1.6. Visually, that negative 2 went over the line. The negative 2 is over here someplace. It went past. Because of that, I have sufficient evidence to reject our null and conclude the alternative. Z equal to a negative 2.16 is sufficient evidence to reject our null and now conclude. And I need to put this conclusion in context. So I'm going to be concluding the following. The proportion of people who feel their financial fortunes are better than their parents is less than 0.78. I don't mean to be a downer here, but your generation has been looked at and they feel your generation is maybe the first one in the history of the United States where the children actually have lesser financial opportunity than what their parents did. All the way back from the colonies up until now, every next generation had more opportunity. But they're saying now that is reversing and it's going back the other way. This particular study from the Wall Street Journal was evidence of that as well. Let's finish now the p-value test. I would find the same z. Again, if you were just doing that p-value test, you would write out the formula, the substitutions, and the answer. I'm just going to go with the answer this time. Our p-value. It's not going to be 2 times something because it's a single tail test. It's 1 times the probability of that tail. Well, what is the tail for 2.16? What I'm really asking here visually is this. If I have a negative 2.16, what is this tail probability? I need to find this probability in here and subtract it from 0.5. So I look for 2.16. 2.16 gives me that middle section from the middle out to be 4846. That means this is 4846. This will be 0.5 minus the 4846. That's what has to go in here. 0.5 minus the 4846. That gives me my p-value, which in this particular case turns out to be 0.0154. We compare that, if you remember, to our alpha level. If this p-value is less than alpha, we have sufficient evidence. If the p-value is not less than alpha, we have insufficient evidence. In this case, 0.01 is less than 0.05. So I have sufficient evidence, just like I did here. I have this keyword sufficient, and I'm now concluding the alternative. So P equal to 0.0154 is sufficient evidence, and the rest would be written right over there as well. Here's an example of a hypothesis test for proportions. Some common mistakes. People will put mu there instead. People will list the wrong formula. They'll go with z and standard deviations, and then they'll say, the problem didn't give me a standard deviation. It's not supposed to. It only has to give you the p and the q. So those are some places where you get caught up. Also making sure your rejection region matches your alternative hypothesis. They're both going to the left. Those are key places for you to have to be really careful. Another example. Hopefully you had a chance to read through this. This is a binomial problem because either the loan was made out to a minority group or it was not. There again are 2 choices, hence binomial. My p hat in this case is going to be the 56 that were made out to minorities out of the 150. Turns out that p hat happens to be 0.373. 3 places is plenty to carry that out. That would mean Q hat would be its complement. I do have a history here, which means they did give me a population proportion historically of 0.35. And that means, of course, that I'm going to be using the Q to be 0.65. They want me to run a test to see if there is strong evidence. Strong would be, of course, alpha to be 0.05. That it's been successful in getting more minority customers. That would mean if it was more, it would mean that we would have more than 35% of our loans going to minorities. That's what we want to show. More is screaming at me single tail. They want me to use a rejection point. That's another way of saying critical value test. So let's just use the critical value test this time. I have a null and I have an alternative. I want to get more loans going to minority, more than 35%. I want the population proportion to be greater than 35% what it's been in the past. This one has to be either equal to and less than or just equal. I'm going to go just equal from what it's been in the past. Step number 2, they said strong evidence. So that indicates alpha is at 0.05. I don't care that n is more than 30 here. This is proportions. I need to look at that greater than or equal to 5. I'm going to use the population estimate, the historic one. I'll use the smallest one. So I'm looking at Pn, is that greater than or equal to 5? P is 0.35 multiplied times n, which is 150. That's going to be approximately 50, definitely greater than 5. So I know that NP is greater than or equal to 5, which means I can use that Z statistic. I need to get my rejection region now. Anticipate a moment. Is it on the right side or the left side of my bell? My bell has the mean proportion to be 0.35. I'm looking if it's gotten greater than that. Greater than means to the right. So my line in the sand has to be a positive Z-score, and it must put all 5% in here, which means 45% goes out there. What is that Z-score? You've seen it before. 0.45 is in there. It's the 1.645. That's my Z-score. If it goes past that, if my Z is greater than that, then I'm in my rejection mode. Okay? Crucial that these two are on the same side. Easy place to make an error. Step number 3, find my actual Z-score. My formula was P hat minus P divided by square root of PQ over N. P hat is the sample proportion, 56 out of 150. That's at 0.373. Minus the population estimate of 0.35. Because I have that population one, that's what I'm going to be using in here. So I'm going to have 0.35 times its complement, 0.65, all divided by the size of my sample, 150. Turns out that happens to be 0.59. It's not close at all to being in the rejection point. Here's the rejection value, 1.6, 0.5 is way back in here someplace. It's fairly close to what our historical estimate was. We really don't have any evidence. It's within reasonable variance. So because of that, I have insufficient evidence. So I'm going to write Z equal to 0.59 is insufficient evidence to reject our null, and thus we continue to assume I'm going to put this now again in context. What am I assuming? I'm assuming the proportion of loans given to minority groups is still at 35%. Assume, I'm going to go with percentage here. Assume the percentage of loans made to minorities is still at 35%, what it was historically. Again, insufficient, continue to assume. Those phrases go together. Another example, I'll let you read through that. Radio Shack is making a claim that they have 21% of the market. We're running a test to see if that's accurate. Notice we're not trying to show that it's more than 21%. We're not trying to show that it's less than. We're simply testing, is that accurate? Because we're testing, is it 21%? That's screaming at me, two-tailed test. This time they want me to run just a p-value test, so that's what we're going to do. Step number 1, the null and the alternative. Two-tailed tests are always the easy ones because the null is always equal and the alternative is always unequal. We have to make sure we don't put mu here. It's the population proportion. Either it equals 0.21 or it does not equal 0.21. We're testing, is that accurate? Step number 2, they gave me an alpha level to be 0.05. I didn't find my p-hat yet. Let's do that a moment on the side. It's going to be 120 out of 700. And in that case, that p-hat turns out to be 0.171. We're estimating the population proportion is 0.21. Because I have that estimate to work with, my Q would be 0.79. I'm going to use the NP to be greater than or equal to 5. NP greater than or equal to 5. That's going to be my N, which is 700, times P, which is 0.21, will definitely be greater than or equal to 5. So I can state that. That guarantees that I can use the Z-stat. If that did not hold for both, we would be unable to run this test. We could not even use a T in this case. Step number 3, I'm going to find my Z-stat. That formula, you remember, is p hat minus p divided by pq all over n. Plugging in, my p hat was 0.171. My population proportion was estimated at 0.21. Because I have that one, that's going to go in for the PQ. 0.21 times 0.79, all divided by the sample size, which was 700. Turns out that that z-score happens to be a negative 2.53. Again, make sure you can get from your calculator to that. Well, where exactly does that show up in this case? A picture of what I'm testing here is the following. I'm testing against the 0.21. I have a z-score. This, by the way, had a z-score of 0 right in the middle. But my particular sample showed up way here on the left. Notice 17 was less than 21. When I do that subtraction, I get a negative. My score, my z-score, turned out to be a negative 2.53. The p-value is that amount right there. What is that tail for a negative 2.53? I have to go to my chart. First of all, it's two-tailed, so my p-value, remember, because it's two-tailed, it's 2 times this tail. I got to consider that it could have gone either direction that far. The tail is going to be 0.5 minus something, right? 0.5 minus whatever this is. So I look for 2.53. On the chart. 2.53 gives me that middle column to be 49.43. 49.43. This tail will be 0.5 minus the 49.43, and I got to double it. That's why when I go over here, it's going to be 0.5 minus the 49.43. So I subtract it and then double it. When I do that, I end up with 0.0114. That's my p-value for this one. I compare it to the alpha. Because it's less than the alpha, that gives me sufficient evidence. So in this case, p equal to 0.0114 is sufficient evidence to reject our null and now conclude that Radio Shack, now watch carefully once, we're concluding that it's not equal to 21%. But we can do a little better than that in this regard. Because it was on the negative side, because it was on the less than side of 21, not only can I say that it's not equal to 21%, I can say that Radio Shack has less than 21% of the market. Had this been a positive 2.53, then it would have been on the right side, and I would have said it has more than 21% of the market. Again, hopefully after seeing this now for the fourth time, you're getting comfortable with the change in formulas. A lot of the other components are the same. Some key differences: you got a P there instead of a mu. You've got a different formula. Other than that, most of the other things stay the same. Now we're going to talk about some understanding of some phrases that quite often come along with hypothesis tests. Okay? What I'm trying to get across here is the difference between statistical significance compared to practical importance. I've gone back to the mean example. So I'm looking at a sample mean, population mean, etc. Let's read through it. Chuck Cash has been the personnel manager for the company for the past 3 years. From a recent scan of the employee records, Chuck feels that over the past 3 years, employees have increased their retirement accounts to an average of more than 31,000. Where 3 years ago, it was at 31,000. He hopes or he wishes to be able to claim at an alpha level of 0.05 that it has in fact increased over 31,000. He takes a sample of 100, and that sample did show that there was an increase, 31,366. Run the critical value test. Well, I'm not going to go to the critical value test right now because I'm trying to establish the point up here in red. If I were to run a critical value test, I would have had significant evidence. I would have had a z-score that would have been statistically significant. I would have had a z-score that would have provided sufficient evidence to reject that it was less than 31,000 or equal, and I would have been able to conclude that it had in fact increased. I'm going to say that again. I would have had evidence that was sufficient to conclude that it was more than 31,000. Okay? Now, look at this statement in reference to what's up here in red. Can Chuck make the claim listing that it is statistically significant? The answer is yes, he can. Here's the claim that he wrote in black. This is not a good claim. It's not written well. 3 years ago, when I began my employment here, the average retirement plan of the employees was at 31,000. Since then, we have made a statistically significant increase of our average amount per employee in our retirement account. Well, we just did the test, or imagine we did, and we were able to conclude that it was more than 31,000. The problem with this statement in red, and if I had you here as partners, I would have asked you to discuss it with a partner. I know it's kind of hard to do that. But the problem with this statement in red is they're using this phrase, statistically significant, as a type of adjective for the noun increase. The way they're using it here, it implies that the increase itself is a large increase. When in fact, I don't know exactly what it is, but it doesn't look like it's a huge increase. $366 out of 31,000, kind of a drop in the bucket. It might be an increase, but we wouldn't say that it's a large one. Watch now how I'm going to say it in a better statement. Since then, we have evidence that is statistically significant that we have an increase to more than 31,000. Our evidence is statistically significant. That means that our evidence has given me sufficient evidence to reject that it equaled 31,000 and now conclude that it's more. The evidence is statistically significant. That statistically significant phrase needs to be an adjective of the evidence, not an adjective of the actual increase. I hope you understood the difference there. It's kind of subtle, but it's kind of important. Same song. Second verse, a little different problem. Same kind of problem though. Chuck Cash suspects that the employees invest more than $100 each month. In the past, it was at $100. So we're hoping that it's more than 100. Sampled 100, got a lot of hundreds there to keep them straight. We find that now the mean is $115 a month, where in the past it was at 100. We're hoping that there's statistical evidence to indicate that it's been increased from 100. He runs the data. Here's a Minitab output. Okay? We're testing at alpha to be 5%. I could run the whole test here, and if they wanted me to do that, I would have had to, but I'm not going to this time. We're just going to look at the p-value immediately and really take a major shortcut. Is the p-value less than 5%? Yes, it is. That means that I'm going to have sufficient evidence to reject the null and conclude that mu is greater than 100. I would have evidence that would be statistically significant that we have an actual increase more than 100. Two statements here. Read both of these and compare which one is better. I'll give you about 30, 40 seconds to do that. The first statement is the correct way to state it. Oops, I got something that came in there. Sorry about that, people. Hope that wasn't there too long. Sorry about that. I'll give you some time to read that again. The first statement is the better phrasing because it's saying the evidence is statistically significant. Technically, it's an adverb there, but it's describing the noun evidence. I think it's an adverb. You English people might correct me on that. Here, it's listed more of an adjective of the increase. This one is not as good because it's implying that the increase is a large amount, when in fact it might not be that big of an amount. Depends if you consider 15 or around $15 a great increase. Some people would say yes, some would say not. But we're not looking at whether the increase itself is large or small. We're looking at how do I use the phrase statistically significant, okay? That's what these two examples were about. In summary of that phrase, statistically significant simply means the likelihood of a particular sample occurring is less than some alpha chosen by someone. This meant that we rejected the statement of the null and we concluded the statement from the alternative. Statistically significant does not necessarily mean the actual difference between the values of the null and the alternative is large. It just means the evidence was less than some alpha level. Finally, the last concept that we're going to look at is just a little bit tougher to understand, The title says Understanding Statistical Significance on Charts. And you'll see this used a lot in the science fields, in the business fields, etc. This happens to be a bar graph done by eHarmony. Okay? So eHarmony is looking at relationship satisfactions. So here's their scale that they're measuring it on. And we're wondering, basically, they're saying here that the relationship satisfaction between their church and their place of worship, and that would be church members, is slightly higher, 5.58 here. You can't see that it's in black, compared to 5.57, a little bit more. The relationship satisfaction on this scale for work and school is less than at eHarmony. Friends and family, a little less yet. Match.com, of course, that's a competitor for eHarmony, less yet. Bars, clubs, social events, less yet. What I want you to notice are these marks right here. This is a addition sign. It has to do with this second one right here. If you can't quite see that, it's a little small. These are stars. That's this one. Notice that the star is saying basically the evidence is significant at a 5% alpha level. The addition sign is saying that it is evidence that is statistically significant at a 10% alpha level. If there's neither star nor an addition sign, we had insufficient evidence. For example, the difference between these two was insufficient evidence. We would have to say, we have no evidence to indicate that one actually is greater than another. On this particular sample, church place of worship was a little higher, but it wasn't mathematical evidence to say one is greater than the other. The difference between eHarmony and work at school, we would say, has evidence that is statistically significant at a 10% alpha level. So there is definitely some evidence there. Not enough to say it's statistically significant evidence at 5%, just at 10%. But now look at the difference from here down to this one. That's a bigger jump. We would say we have evidence that there's a difference that is statistically significant, the evidence at 5%. So there's evidence at 5% that would be statistically significant to say there's a difference. We're not saying how big the difference is, just that there is a difference from here to here. Again, there would be evidence that is statistically significant that there's a difference between the two, as would be with the last one. No evidence here. They show that basically it's like running a test here, running a test between these two, test between those two, and a test between those two. And they're showing the results by simple marks up above with a key. Another example of that. If we're looking, this is a medical one, the average LGE score. I got to be honest, I'm not even 100% sure what LGE stands for. But I wanted the graph here just to show you something in this case. Notice I have a mark here that says the proportion is less than 0.05. In this case, that's standing for the p-value. The p-value is less than 0.05. They're saying there is evidence that is statistically significant at alpha to be 0.05. There's a difference between the aorta and the coronary arteries in this time interval. Notice in this time interval, there's no star up there. That means there's no evidence that is statistically significant to indicate any kind of increase or decrease. For all we know, they're equal. In fact, it might even be the coronaries could in fact be greater than the aorta. This one, again, it's quite a ways. So that's why it shows up as there's a difference between the two. We have evidence that is statistically significant that there is some type of difference between the two. We're not saying how big the difference is, just that there's evidence to indicate there is a difference. Here there was evidence to indicate a difference. Notice this one would be from here to here. There's evidence that those differences are in fact different. Kind of confusing, but you'll see a lot of charts with those kind of marks in them. Those can be important because they can give a ton of information with just a few tick marks. Basically, they're showing the results of, in this case, 1, 2, 3, 4 separate hypothesis tests. And they're giving you the overall result in a very quick, short format. That is all we have for today. Again, I'm assigning this section 9.4 on this Friday. It'll be due next Wednesday, which I believe is April 8th, if I'm not mistaken. Okay, have a good rest of your day.